Yeah, so the next session will be about optical atomic clocks. I will start this session today, and I will try to introduce a concept and basic idea how the optical atomic clocks works. And then tomorrow, Jerome Lodewijk will give you more technical details, and after that, Fritz Riele will tell you even more details about the clock laser. But I hope that after today you will be prepared for the next two lectures from the fundamental science, because I hope that we will know how the clock is operating. So I'm from here, from Nicolaus Copernicus University, and from National Laboratory of Atomic and Molecular Physics. And I will start with definition of the second, that probably all of you are aware that we define second by the transition between two energy level of atoms, or specific atoms, cesium-133. And the point is that this transition is between two hyperfine levels. So the second now is based on the microwave transition. And this, introduction of that definition was a really breakthrough in thinking about time, and this definition was good enough for a long time, and maybe it's good enough still now. But during the whole years, making a better clocks was always connected with making better economy, better life, and better science. So the question is, who needs a better time now? Because this definition based on cesium is still quite good. And well, there are several areas that can be better if the time will be better. The satellite navigations need really precise time. Telecommunications needs really precise time. But for these two areas, probably the time that we have now is quite good. But if we go further to the deep space mission, then perhaps the time based on the hydrogen masers and cesium clock is not precise enough for the satellites that are not, really around Earth, but at some, deep space. Time is really needed in transport, in commerce, in stock exchange. Just something like half a year ago, a small country in Asia above something like 1,000 PTP time servers, just to cover the really small country, about something like more than 1,000 PTP servers to cover all stock exchange and banking in the country. As I'm aware, is $60 sum to buy this. And I believe that at the moment the most important applications of the clocks is the fundamental science. Because experimentalists measure something, and the more precise tool for measuring, the better results he can get, or she can get. But there is also something that it's called smart grid that can really save a lot of money to split in the really nanoseconds time between different area of country where we should put the power from the power station. And there is also a geodesy, which is not really connected with time, but rather by using the clocks as a sensor of gravitational potential. Just a nice picture, but to support that, first we can have this, some really documents what is the market size in this or the future, in this year or the future. I'm not 100% sure if the billion are imperial or European. It depends on the source, but I mean there's just there's just advertisement. But now I have to prove that they really need that that time, and that's the proof. That's the list of supporters from made 4 years ago for the project Optical Clocks with 10 to the minus 18 uncertainty. And the letters of support for that project came not only from from the Times community, but you can see that 3 letters came from space agencies. Well, mostly, actually, the most important is ESA. And you can see that 4 letters came from geodesy and oceanography, which is strange. Why oceanography needs a time? It's because the climate in Earth is ruled by a really big flow of water through the oceans, which is really deep, alluvial flow of water that is really hard to observe. This flow of water. There's some probes, deep ocean probe that can measure that. But they really hope that with the optical atomic clock precision, they will be able to measure the changing of the Earth, the gravitational potential due to this flow of big masses of water in the oceans. And because of that also, at least two geodesy institution and International Association of Geodesy is also really interested in that, because there, as far as I know, there is no other tool that can measure the gravity potential. What we can measure in casual way is acceleration due to gravity, but not the potential. And if you combine 2 methods to measure the potential and gravity constants, local gravity constants, you can map exactly, for example, was the some oil source beneath ground, or you can check before volcano erupts. Then when the lava goes to the volcano, there is some change in potential, and clocks can measure that. And also, these 2 telecommunication company, one is Orange, one is British Telecommunication Supports. So I believe that's some kind of proof. I mean, because they are business. So if business believe that optical clocks can help them, then I treat it as a proof. And about fundamental science, there is JIVE, which is one of the few VLBI networks. And the VLBI network is very large base interferometry network, the network of radio telescopes that most of the cases work in such a way that each radio telescope locally observe the sky and record observation with some timestamps. And then the data are sent to one center that cross-correlate all the data, and from that you can have one big picture. And the point is that the timestamps require quite a good precision. I mean, first small network were made with rubidium standards, but nowadays all radio telescopes are equipped with hydrogen maser, which is good enough for most of the cases. But now, we make bigger dishes with the better surface quality, and the better surface quality, the smallest wavelengths we can use for detection. For sub-millimeter wavelength of radio telescope detections, it seems that hydrogen maser is no longer enough to correctly put the timestamps. And that's why we can use optical atomic clocks. I mean, even here in Torun, we made some session already with the optical clocks instead of hydrogen masers. There's a proof of principle, and they were quite happy with that. Okay, so that's the basic concept of atomic clock. And the ideal clock should provide you a signal with stable and universal frequency. I mean, universal means that the same clock made in the same way should give you the same time in every place of Earth, of universe. There's a big assumption that if we take an atom and somehow isolate or shield from any external perturbance, it should have the same structure of energy levels in all places of universe. So that would make you the ideal standard of frequency. So that's the standard. Actually, it's not the clock, it's a standard of frequency. I mean, something that you check what is the correct frequency. And to have the correct clock, you need two ingredients. You need a harmonic oscillator, a pendulum that keeps oscillations all the time at the same frequency, and you need a watchmaker, the guy that told you that your oscillations indeed takes 1 second. So all our clocks have, inside there's some kind of pendulum, like quartz or something like that, or spring, and our clock needs a watchmaker. So we have to either use GPS or listen radio with that put a timestamp, or our mobile phone has a watchmaker from our provider. And in the atomic clock, the watchmaker is the atom. Yeah. So the pendulum is a laser. So we have a laser made to have a precise frequency all the time. With that laser, we interrogate energy structure of atom, and if the frequency of the laser does not fit exactly the frequency of the transition, we set a correction to the laser. That's how any atomic clock works, not necessarily optical. And for every clock, we can set that if you have some ideal frequency that should be precise by definition, what we observe is always something else than the ideal frequency. And we can write down that there is some factor that shifts the frequency and some factor that adds some fluctuations around the correct frequencies. And with that, we can set about two quantities, accuracy and stability. Accuracy is the uncertainty of this shift, and the stability are the statistical properties of these fluctuations, usually characterized by the Allen deviation. And these two quantities are really connected to each other. So to have the really good accuracy, to make the good accurate clock, so to correctly quantify uncertainties of this fractional offset, your clock must be stable. So you cannot quantize the offset better than your stability. Yeah, so that's the picture from NIST that, well, probably you've seen, or one of other variation, that clock, if you plot the frequency measured by our clock over time in comparison to the correct frequency, we can have the clock that is stable but not accurate. We can have a clock that is shitty, so it's not stable and not accurate. We don't call it clock. We can have a clock that is accurate because if we average over time, it would give us the correct frequency, but with huge fluctuations. We have a perfect clock that is both stable and accurate. Yeah, The stability of the clock is described by the Allen deviation, which will be fully covered by Jérôme Lodewijk tomorrow. So all the details will be tomorrow. It's just, a hint here that we plot how the noise behaves in time by averaging over different time scales. And well, there's a lot of information hidden here. For example, what noise type we have in our clock, but that will be covered yesterday. We don't need that to understand how the clock is working. Yeah. So, what time standard people are using now? The primary standard made by of atomic fountains. There's several atomic fountains worldwide that send its time to one place, and at that place take the average of the frequencies from these atomic fountains and send the correction back. And the accuracy of that atomic fountains is now on the order of log 10 to the minus 16. If we have money, we can go to the shop with clocks and buy a commercial cesium clock, available in any shop with clocks. And the cesium clocks have good long-term stability, so 10 to the minus 15, after averaging over a few months. And the accuracy at the level of 10 to the minus 13. So this fractional accuracy, so it's just delta frequency over the frequency. So deviation of the frequency by the frequency. So this fractional, there is no unit here. And I believe that most of the clock worldwide are now hydrogen masers. There's 2 points, fountains and clocks. Fountains usually use cesium. It can use rubidium also, but mostly they use cesium. And the cesium clock use cesium, is obvious. So there's 2 stuff work on the definition. So you can really have a legal time from them because they use the standard as a frequency reference. And the hydrogen masers unfortunately use hydrogen, so it must be referenced back to the cesium. But nevertheless, it played the role of the local oscillator quite well because it has much better short-time stability than any cesium clock. So it has 10 to the minus 15 over a few hours. So the popular solution is to have both maser and cesium clock and correct hydrogen maser every day or every few days by cesium clock, or maybe not over a day, maybe over several days, I would say. So that's the picture of the clock. This clock is the most popular clock worldwide. It's really old technology. It's sold from several tens of years. We're just changing the names and manufacture, but with the same construction. And there are several sellers of hydrogen masers that you can go to the shop and buy. And well, the good thing is that you can just buy, put on the shelf, and it will be working. You don't touch it, and you get the frequency. Unfortunately, that's not the case with the atomic fountains and optical atomic clocks yet. But if we compare the quality of the cesium clocks and hydrogen masers and optical clocks, the difference is huge. So here is the stability pictures of some, cesium clocks and some hydrogen maser. I believe that nowadays, it's 10 years old picture, so now the hydrogen maser, I believe, is 1 order of magnitude better, minus 15, but still, minus 15 somewhere here. And if we take the stability of the state-of-the-art optical atomic clock, after 10 seconds it starts at minus 16. And it goes down below 10 to the minus 18. So you can see that is 3 orders of magnitude on much shorter time scale. We can also take some relatively new data from the atomic fountain, from CERT. You can see that our tomorrow speaker is the first author here. The atomic fountains has better stability than the hydrogen maser, but still it can go down to the -16 after 100,000 seconds, which is the point where we are after 10 seconds with optical atomic clock. So that's unfortunate that to really tell how good your clock is, you need a second clock. So well, if you have an optical clock, honestly, to tell how good this clock is, you need at least 2 optical atomic clocks. So if anyone wants to build an optical atomic clocks, it's better to make 2 at the same time. Okay, so that's also quite a new picture of Safronova showing the accuracy. So it's not the stability, it's the accuracy of the clocks, of the microwave clocks. And you can see that already something like more than 10 years ago, optical clocks surpass the microwave clocks. So probably now is a good time to think about the new definition of the second. And indeed, there are really advanced work towards redefinition of the second. Okay, so why the optical atomic clocks are so good and shiny and much better than the microwave clocks? So the quality of the clock is defined as the ratio of the frequency and the width of your line and signal to noise in your measurement, which is, well, at some point proportional to the frequency and time of your averaging. And the stability of the optical atomic clock depends on the quality of your clock. So the better, I would say that should be probably instability here. Yeah. So the better quality, the better stability, the worse instability. So my error here. So here is the TC is the time of clock cycle. You see, you remember from the generic clock, you have your clock that was used to interrogate your atoms. And then the correction was put to the clock laser. So there's cycle walk. So each clock cycle takes some time. And tau is the averaging time. And sigma spectroscopy is a factor depending on the spectroscopy that you are using to lock your clock laser to the spectroscopic line. And actually, in fact, here also is sitting this TC, but it's not really important. What is important is the Q here. And there is also the hard limit, that is quantum shot noise limitations. So you can see that the stability of the optical of the atomic clock depends not only on the quality of the clock, but also of the number of atoms that you are using in your system, because of the quantum mechanic properties. And what is obvious is the better frequency, the higher frequency, the better quality of your clock with the same width of the line. And optical transitions, have the frequency much higher than the microwave transition. And that was the truth that people know from the start. The problem was that microwaves is easy to be counted by electronics. So the cesium clocks give you gigahertz range that you can count with electronics. And to count the optical transition, several hundred of terahertz, at the moment is not possible with electronics. So the optical clocks doesn't have any chance before somebody came with the idea of the optical frequency comp and get the Nobel Prize for that after that. But now we have this optical, thanks to the Hensch, we have optical atomic clocks. and we can count optical frequencies, so we can use much higher transitions, much higher frequency in optical transitions.
So Michał, this last line, are you still referring that to the standard quantum limit?
This is just the short noise.
Shouldn't that be the square root of number of atoms?
I think you're right. Yeah, I think you're right. Yeah, there should be square root. So at the moment, there are two main types of optical atomic clocks. We can use trapped ions, and we can use neutral atoms. I believe in all practical realizations of the ion clock, we use single ion clock. There are no works with the Coulomb crystals that we can use several ions captured in the crystal, but the standard ion traps well, have just one ion trapped in the pole trapped by RF field. And this trap, because it's trapped really tight in the electromagnetic field, is really isolated from the external perturbation and has excellent stability, excellent accuracy. Here should be 19, I believe. So sorry, my fault. So it is 19. So we are below 10 to the minus 18 with the ion clock, and they have pretty good stability, but unfortunately restricted by the quantum short noise because there is only one ion. And I will not talk more about ion trap because the school is about cavities, and the cavities are not used in the ion trap. The cavities are used in the neutral atoms traps. So we can use optical lattice to trap thousands or millions of neutral atoms, but at the price of the high perturbation due to AC stack shift from this optical lattice. But if we take care about all the perturbances, we can have them well under control, and the stability of the best clock now is, accuracy of the best clock now is at the level of 2 times 10 to the minus 18. And because of the high number of atoms, high stability is possible, and I believe that the record is 1.5 times to the minus 16 on 1 second, which gives at some averaging 3.2 times to the 10 to the minus 19. Okay, so how to build a clock? To make an optical clock, we need a good transition. So we have to carefully choose 2 atomic states that give you the standard of frequency. And the natural light width of casual electric dipole transition is usually bigger than 1 megahertz, which would give quality factor below 10 to the minus 8. Because the quality factor depends not on the frequency, but also on the width of the line. There is a ratio there. So we need a less probable transition. So the clock transition should be narrow. Basically, it should be as forbidden as it can be, and should be mostly insensitive to the external field to have a good accuracy and statistical I forgot the word. Properties, statistical properties. So the possible candidates are, well, people try. That first is just a 2-photon transition and higher order electron transitions, like quadrupole, octupole transitions. We seek a low energy nuclear transition that we know that there is one in thulium-229. We know that there is this transition, but we don't know exactly where. And it's really
0.17 electron volt current uncertainty.
So it's still
Well, it's very small.
Okay, so, but that depends on your point of view. I mean, that would be really good candidate for the clock, because the transition not between is not electronic, is a transition in the nucleus, so it can be easily shielded from anything outside. But in optical atomic clocks, we still use intercombination transition, so the transition that requires spin flip during the transition. And what we're using is the earth. Alkaline earth and alkaline earth-like atoms or ions, which basically is magnesium, calcium, strontium, hydrogen, and ytterbium. And all these atoms have really similar structure of the lowest states. There is a really strong 1s0, 1p1 transition, and there are two possible intercombination transition to 3p1 and 3p0. I believe that Florian already showed that yesterday. And 1s0, 3p1 transition is forbidden, but slightly allowed because of the fine structure interaction with 1p1 state. And 3p0 state in fermions, even if it's double forbidden, because of the mixing between 3p0 and 3p1, so because of losing LS coupling, it is slightly allowed in fermions. In boson, it's still completely forbidden, but if we artificially somehow couple these two states, for example, by adding a static magnetic field, it can be made slightly possible to make this transition. So you can think about that in fermions, this transition is possible because of the existing magnetic field from the nucleus. And if there is no such a magnetic field, we have to add this from the outside, which has advantages and disadvantages. Advantages are that we input a quadratic Zeeman shift to our transition, so any variation of the magnetic field will put the uncertainty in the shift, the quadratic Zeeman shift. But on the other hand, we can tune the width of the transition by changing the magnetic field. So we have a knob that can tune the width of the transition. Okay. So yeah, we have atoms. Let's try to make a clock. So let's try to make a spectroscopy of the atoms. And we will try to make a spectroscopy of this transition, which is 1 millihertz transition for sure, for example. We can see that it's not easy, because we just shine the laser to our transition. We will see that at room temperature, because of the Doppler shift, the transition width is of gigahertz in the room temperature of most of the atoms, which is quite easy to calculate, because if you take the Maxwell-Boltzmann distribution for the speed of atom, there is a broad distribution of the speed. We can put a Doppler shift to that distribution, and we can calculate the distribution of the frequencies. And after some short calculations and derivation, we get the Gaussian profile, which is gigahertz in room temperature. So there are two solutions. First, we can think about some tricky spectroscopic methods like subdoppler spectroscopy or two-photon spectroscopy. Or we can cool down atoms as low as possible. But still, the Doppler shift is only the first order effect. The the second effect that really kills the idea, even with cold atoms, is the recoil shift. Is the fact that the atoms, after emit or absorb a photon, they give a kick in momentum. So if we plot ground and excited state of the two-level atom, and so that's the ground of the excited state. So instead of two levels, if we add the momentum, we will have a state that the energy, including momentum, depend on the velocity. And after the atom absorbs a photon, it gets a kick that transforms it to the new excited state that includes the momentum taken from the photon. So we have somehow to think how to get rid of the recoil. So now there will be some equations. Sorry. If we take the Hamiltonian of the atom in the Schrödinger picture, we can write down for the ground and excited state. And if we choose the zero energy at the ground states, we can simplify interpret Hamiltonian to the simple form. And then we add electromagnetic field to our two-level atom. So let's shine a monochromatic electromagnetic wave with frequency omega and some phase. And let's assume that we have the dipole interaction with operator of D that is charge times R, and it can be expressed in this form. So if we add to the Hamiltonian, we can write down the interaction Hamiltonian in slightly more complicated wave. So we just write down this, including this form and this form. So we put this here and this put here. And we define here the so-called Rabi frequency. And the Rabi frequency is the rate of transition between excited and ground state if we shine all the time on atom. Since it's complicated, we should make the rotating wave approximation to simplify this slightly. But actually, to correctly make the rotating wave approximations, we should go from the Schrödinger picture to interaction picture. So we should treat this interaction Hamiltonian with unitary transition that is defined as E times EH0 T divided by H. Then, well, we can write down this as, I believe, ground plus I omega 0 T divided by H E. So if we take this, put to the interaction picture the whole Hamiltonian, there will be, we'll get 4 layers of equations. Then we can think that we are close to the resonance with our laser light. So we assume that the detuning of the laser from the transition frequency is much lower than the frequency transition. So after we make this transition, there will appear here a lot of factors with E omega 0 minus omega or E omega 0 plus omega. And what we assume is that this part is really fast and will average over time. So with average over time to 0, we just, get rid of them. And then after we go back from the interaction pixel to the Schrödinger picture, so by the opposite transition, unitary transition, we will end with this simple rotating wave approximation Hamiltonian, which is here. I mean, I just wanted to tell you because that is really, at the first glance, look easy that we came from here to here just by getting rid of two forms. But it's not true because there's quite advanced math involved here to get this rotating wave approximation. So if we define generalized Rabi frequency that include both Rabi frequency and the tuning, then we can solve that and get the probability of finding the atom in the upper state as a sinc function. So all this math to get one probability distribution. And if there's a sample of atoms with decoherences, and if we have enough decoherences in our sample of atoms, that can be approximated as a Lorentzian line whose width is determined by this decoherence rate divided by 2 pi. So in fact, the Doppler shift gives you not the Gaussian but the Vogt profile. That is a convolution of Lorentzian and Gaussian profiles. And now let's put our atoms in the harmonic potential. We're still thinking about two-level atoms in the electromagnetic field, but now we put that in the harmonic oscillator potential. So we have to add a new term in Hamiltonian that corresponds to the frequency of the harmonic potential, and lowering and creator and annihilator operators that move the atoms up and down in the ladder of Hamiltonian state. And if we include this equation in the Hamiltonian with the rotating approximation, we will get a modified Rabi transition, rate of transition in two-level atom from some ground state that is on n level of the harmonic oscillator to some excited state that is on m level of harmonic oscillator in the quite complicated form that is present here, where eta is something that is called lamp decay parameter that depends on the harmonic oscillator frequency and wave vector of our electromagnetic light. Okay, that transition from Gn to Em correspond. You can see that actually you have some ladder of harmonic oscillator states from the ground state, and another ladder from the harmonic oscillator for the excited state. So if your atom in the ground state is somewhere here, for example, on n equals 0, it can go to the, let's say, +2 or 1 or -1 state. And if the distance between these states is big enough, we can see that in frequency of in the units of the trap frequency, of the harmonic trap frequency, so here probably should be omega osts, OSC. It's not the transition, so it's probably the big picture. This should be this omega h, yeah? That's the frequency. We can make a spectroscopy and we can see that there are resolved psi bands. But that will be only if this eta is much, much smaller than 1. If we calculate this Rabi frequency and put that to the spectroscopy signal, we can see that independence of eta our signal, I mean, the bigger eta is, the more our signal actually look like a Gaussian due to different recoils from our photon. But the smaller eta is, the more resolved psi bands we can see. Yeah.
Sorry, I got a question. So each of these peaks is one transition, right? From
Yeah.
1 to.
So let's say that's the transition that does not change the
How are they like 5? Isn't there like a selection rule?
the lattice.
There are like 5 peaks in the one total.
Yeah, but why not to jump from here to here?
I mean, it's like an excited state from. Okay, it's like.
I mean, I don't think that there are rules that you cannot jump a lot.
Is the kinetic energy of the atoms.
Ah,
Yeah, the only difference between this picture here is that here you have a continuous spectra of possible momenta. And if you add the harmonic oscillator, you no longer have you quantize your momenta. But still there are no selection rules. I mean, you have big enough energy, you can go 100 states. And for example, you can remove your atom completely from the trap. And for example, in the zero peak, there is no recoil effect at all. And if somebody can think, what about the momentum conservation, or how about the energy conservation? And he's right to wonder why is that, because energy and momentum must be conserved. And you can think that the momentum and energy are taken by the lattice, or this harmonic oscillator. I mean, something that keeps the harmonic oscillator in place. So in the atomic clock, you have a lattice with a lot of that potential. And I believe that in the end, it goes to the mirrors of your cavity. So it's starting to be a macroscopic effect. OK, so here we have an optical lattice that we use in the clock. An optical lattice is made of two counterpropagating beams, or just a one cavity that gives you in one direction a periodic structure of trapping holes and the Gaussian profile in the transverse directions. And if it's red detuned, it can trap atoms, as Florian showed you yesterday. In practical realization, often we put the cavity because it also play a role of power build-up cavity. So you can have much bigger intensities inside the trap, so the trap can be stronger than you just take one beam and retroreflect, which generally is not what you really want to have, because all this, all this AC Stark effect that shifts your line. So you don't have, you want to have deep enough potential to capture the atoms, but not too big, because then your clock is no longer a good clock. Anyway, optical lattice potential can be approximated, at least in the low part, by harmonic potential. And if we have this optical lattice potential and we go again back to the 2 level in the electromagnetic field, we can input the dipole moment of the atom, which is depending on the complex polarizability of the atom. The polarizability can be induced by electromagnetic field. And we can write down the potential of interaction between light and this dipole moment. So that's E actually is the intensity, is the electric field of our optical lattice light. We can write down the potential of our dipole trap. Does it depend on the real part of the polarizability of the atom and intensity of our trapping light. And the scattering light that causes losses in your trap depend on the imaginary part of the polarizability and intensity of the trap light. if we take the really classical Lorentz oscillator model of atom with some damping gamma, we can somehow approximate our polarizability by solving the other equations as are this form, where this gamma depends on frequency of the transition, frequency of the lattice that is driven the Lorentz oscillator, and the losses, I mean the friction inside our Lorentz oscillator. And after again making rotating wave approximation, which I believe here is much easier because you can just, write down in the form of sum and differences between omega 0 and omega. You can end down with really simple form of dipole potential and the scattering rate that depends only on gamma, detuning, and intensity. And what you can learn from that approximation is that the interaction potential is proportional to the light intensity, and the sign of the potential depends on the detuning. So if you are redetuned from the transition, the force is directed to the potential maxima, and if the detuning is if it's the blue detune, so the frequency of the light is bigger than the frequency of the transition, then the force is directed to the potential minima. And so that's why the most popular lattice for the clock is what we wrote before, is the waist with the lattice inside. Yeah, but the price is that the atoms are trapped in the maxima of the potential. So if we plot 0 and I max, so we put the picture, the atoms are trapped in the maximum of the potential. So that means they are placed in the place when the AC stark shift and all shifts connected with the light are the biggest, unfortunately. The possible solution is to use the blue datum trap. So to make a trap that the atoms are trapped in the minima of the potential, but you can easily see that in one-dimensional it's not so easy because there is no trapping force outside. So you can either make some high Laguerre-Gaussian mode to put, well, a ring trap around, which is possible, but really hard to do. Or you can make three-dimensional trap from the blue light, like Katori, for example, would have done. So the blue datum trap seems potentially better, but it's much harder technically to make. And when we make a clock, we want to make it simple, stupid, to be able to copy-paste in the whole world like the cesium standard.
What is the difficulty in making the Laguerre-Gaussian mode?
Yeah, for example, you need much bigger power to capture the atoms. And then you cannot make the power build-up cavity for Laguerre-Gaussian like that because it will change the phase in such a way that will interfere in the wrong way. So to make a power build-up cavity for the Laguerre-Gaussian, you need to make a for example, bow tie cavity to really make a power build-up cavity for the Laguerre-Gaussian mode. And also, I mean, it must be really high order Laguerre-Gaussian mode, because you want to have a really steep potential of the border. Because if you don't care, I mean, the potential will be quite weak. But anyway, there are traps made with Laguerre-Gaussian mode. Like, for example, in Innsbruck, they make the so-called ghost trap that consists of the Laguerre-Gaussian tube, but not for the clock, for BC. So the ghost trap was made of a tube and the evanescent mode, evanescent light on the prism, and the gravity. So the atoms can bounce from the evanescent weight and be trapped in the trap. But it was actually 15 years ago. By Rudy Grimm.
As you said, no cavity, so
Sorry?
there was no cavity.
Yes, but they can use the really powerful laser to do that. Yeah, it's true. Oh, and also the second thing that we can learn from these two simple equations is that since the scattering depends on the square of the detuning, it's better to have large detuning and high power of laser, because then the scattering gets lower and lower. Okay, so that was what I said, that the most basic optical lattice trap consists of two focused counter-propagating gray-detuned laser beams with wave vector k and minus k. And then the intensity of direction of propagations is standing wave after short calculations. And the potential in the direction of the propagations of this beam depend like a cosine square. And if we take a focused beam, we get the one-dimensional optical lattice with the potential that is Gaussian in the radial direction and the cosine square in the axial direction. And if we put that to the Hamiltonian and we probe two-level atoms in the lattice probed by the clock laser with omega p frequency, we can have this Hamiltonian. And this Hamiltonian, as Florian said yesterday, corresponds directly to the Bloch state known from the solid states. And as we know from the solid states, we know that the solid state, there are no, in the crystal, there are no energy levels, there are energy bands. So if we go to the quasi-momentum picture from the solid state, we can have a Bloch states. Okay, so I don't remember, you're familiar how you construct the Bloch states. If you go to the momentum, the quasi-momentum picture, you can think about your state as a series of potentials. Then you can make a cut because of 2 pi duplication is the same exactly. And then you end with the bands with anti-crossing here. So that's basically what create you the bands in the solid states. That's why it looks like that. And bigger potential are the flatter states you can get. And you can think about Wannier-Stark regime that these bands came from tunneling between lattice sites. And if you allow tunneling between lattice sites, you're no longer in the lamp decay regime. Lamp decay regime was this funny trick to get rid of recoil. In lamp decay regime, there is no recoil because, well, let's say the potential takes the recoil. But if you allow atoms to actually move, to tunnel, they can have the recoil. Okay, so one method to fight that is to go to the highest possible potential, because the higher potential, the more tunneling is suppressed. And sorry about the French, largeur de band, so the width of the band, independence of the potential of the lattice in the recoil energy. So it can get smaller with the recoil energy. I believe that you must have at least 300 recoil energy to get rid of the recoil, to suppress tunneling enough to be at the level of -18. Or you can think a little and make your lattice vertical. If you make the lattice vertical and you are standing on the earth, not on this, and you are not in the free fall like in the ISS station, then you can add to your Hamiltonian another potential that came from the gravity. And then each of the lattice site has slightly different potential that completely suppress the tunneling. Because, for example, atom cannot tunnel up to the different energy state. And that's called Wannier-Stark regime. And that's a picture from our lab, from the 88 strontium atom trapped in the lattice. And this is the clock transition spectroscopy. You can see that that's the huge peak is because the transition from the same level to the same level of the harmonic oscillator state. And on the right and the left hand side, you can see sidebands that correspond to the atoms that after transition land in the higher or lower harmonic oscillator state. And you can see that they are not exactly on the same height. And that means that the atoms are cool. Because if you think that all the atoms were in the lower state, after transition they can be also in the lower state or in the +1 state. That cannot go to the -1 state because there's no -1 state. So if the atoms are hot, is somewhere in the middle of the ladder of the state, these two sidebands are more or less on the same height, because there's some probability that the atom can go up or down in the ladder of the harmonic oscillating state. If the atoms are really cool, most of them is in the ground state, the sideband that corresponds to the -1 transition is really low, because only few atoms are in the excited state. So from the ratio of this amplitude, you can calculate the temperature in the axial direction of your trap. Also, you can see that these sidebands are much broader than the zero carrier. It's because that we are in the 1D focus beam, and in the direction of in the transversal direction, we are trapping the Gaussian potential. So if the atoms are hot, they can go, they climb up in the transversal direction of the Gaussian, and the higher they are, the more anharmonic potential they see. If they are in the harmonic potential, the frequency of the transition is not exactly the same. So from the width of these two sidebands, we can calculate the temperature in the transversal direction of the lattice. And that's a funny thing, that you can see that the temperature of the same sample of atoms in the axial and the radial direction does not necessarily must be the same, and in general is not the same. Okay, so now let's move to the actual experiment. That's a typical vacuum system of a lot of clocks. There is some Owen atomic source. This really similar picture was shown by Florian yesterday. This Owen with some sample of the clock, with some sample of atomic sample. For strontium, it's heated to the 500 Celsius centigrades. Thereafter, some nozzles have a beam of atoms that can be cooled down here in transversal direction by 2D mode, if you want. Then there is Zeeman slower that slows the atoms from 450 meters per second down to the 30 meters per second, which is low enough that can be trapped in the scientific chamber by the magnet-optical trap. The fourth Earth-like alkaline atoms. In most of the cases, we have two stages of cooling. We first use the strong transition, first stage cooling. That you can see that the strontium in terbium is of the order of 30 megahertz. And as Florian told you yesterday, it can cool down to something like 1 millikelvin. And then we load the atoms from the blue mode to the red mode, which is made on intercombination transition from 1s0 to the 3p1, which, for example, in the strontium case is 7.6 kilohertz. That means that you cannot take a diode laser off the shelf for the red mode transition, because off-the-shelf laser from Optical or from any company, it's something like 100 kilohertz. Am I right? Yes. Optical technicians tell that I'm right. So you have to narrow it somehow, and you do that, for example, by optical cavity, and narrow it to this 1 kilohertz, and then you can use it as a cooling laser from the mode.
Why do you need to do another trap? Why can't you just switch the lasers on the same trap?
I don't know if I showed it already. Probably it was somewhere. The point is that the optical trap that we use are quite shallow. They cannot trap atoms that are too hot, and 1 millikelvin in our trap is way too hot to be trapped. Actually, one can make the lattice, or one can make the trap that is strong enough to capture the atom that has 1 millikelvin, but the intensity has to be quite strong, and the tuning to the transition must be quite low. So all the AC Stark effect and all the light shift will be enormous, so it will give you a really, really bad clock. So in fact, we use quite shallow lattices to not perturb atom too much because of the light. And that's why we need to cool down atoms as low as possible, ideally to the ground state of the optical lattice. Notable exception is the mercury. In mercury, the intercombination transition is 1.3 megahertz. So we don't need to use the first stage cooling because with this weak transition, we already able to capture the atom from the vapor or from the beam. And on the other hand, the mercury is heavy enough to have quite low recoil temperature limit, so it can be cooled down low enough, even with 1 megahertz transition, that we still are able to capture that in the optical lattice. Okay, there's some technical problems, as always. The real atoms in the vast majority are not two-level atoms, so there's always some atoms that prevent, some levels that prevent us from making just one light working magnet-optical trap. And in case of our 1s0, 1p1 transition, there is some 1d2 transition that part of the atoms from here can go down to this 1d2 states, not too much, 1 over each 100, I believe, but it's still visible. And then from that state, it can de-excitate to the 3p2 or 3p1 state. If it de-excitate to the 3p1 state, it's okay, because then it can goes down to the ground state. But the 3p2 state is metastable. I mean, if the atoms came here, it will stay here. More in the bosons, also this state is metastable, so if it goes here, it stays here. But fortunately, it goes only here, because that transition is also forbidden. So we have to clean up the state. So we have to add some repumpers to our system, as in most of the magnetic optical trap. And one of the solution, not only one, but one of them, is to add 2 lasers that optically pump from 3p2 to 3s1 state. I believe that is most popular solution because the diodes from these 2 frequencies from the strontium are quite cheap. And from this state, it can go to 3p1 and 1,0 state, or it can go to 3p0 state, which is metastable. That's why we need the secondary pumper to pump up again up, and then after some reasonable time, all the atoms go to the 1 and 0. Okay. As I said, with lambda deeper regime, to be still in lambda decay regime, we need a potential depth around 10 recoil energy. So we need a strong trapping light to do that. And because of that, we have a huge light shift, which are at least several tens of kilohertz. So your transition, your millihertz transition will be shifted by several tens of kilohertz, which is also will not make a good clock. So the solution is so-called magic wavelengths, but that will be covered by Jerome tomorrow. Okay, so that's all the lasers that we use in our system for making the clock. So there is a dipole trap, the beams that tune for the mode enzyme are slower, this red mode, 2 repumpers, and the laser for the clock transition. Just be aware that for 87 for fermions, as Florian told you before, there are actually 2 different frequencies here. So either 2 lasers or 1 laser that is additionally shifted by gigahertz. Okay, the clock laser will be covered tomorrow also in the session 3, but to get you feeling how the clock laser is made, we have a laser. It can be the diode laser, it can be a fiber laser that is locked to the high Q ultra stable cavity. If you take high Q cavity with the reflection coefficient 0.99995, it gives you the spectral width of the teeth of the mode around 1 Hertz. And you can lock your laser on the top of the mode, so you easily can go with your laser below Hertz. That's dependent on the signal to noise. And you have to apply some fast feedback to your laser. In the case of diode laser, it really must be a fast feedback. And that somehow is a technical problem, because even if you learn at school that diode can be tuned really fast, that's not necessarily true for all diodes, because of the capacity of the junction in your diode that sometimes filter out high frequencies. And to make a correct closed loop, you need to put much more power to the high frequencies than for the low frequencies. And for example, the optical Falk module does not allow you to tune that too much. So you either make your own lock system, or you can buy from the company, also from Optical, a selected diode that they know that is good for high frequencies and that doesn't have this problem with capacity. Okay, that's a, well, a cavity looks like that. It's not a really good cavity, but the cavity anyway. And as you will learn tomorrow, the best cavities in the world has a distance set between two mirrors such that the mean distance between these two mirrors does not change more than the size of the proton. It's always, I mean, it's always unbelievable for me. Okay, so that's the timing scheme of one cycle in the bosonic clock. So first you start with the blue mode, then you have the red mode, then you shine your clock laser to your atom. So actually that's what is important, that you shine your clock laser to your atom to check if you have the correct frequencies. And you are not making the spectroscopy. You just shine your laser to the atoms with the hope that you excite some of the atoms. And then you check with the detection if any of your atoms were excited. So it's not really making a casual spectroscopy. You just shine on the atom. We just call it interrogation. We ask the atoms if we are the correct frequency. And then check with detection if any of the atoms get excited because of that interrogation. And you can see here that there's a difference between bosons and fermions. That's picture for bosons, and that's picture for fermions. So for fermions that have hyperfast traction, you actually have to have you must make at least 2 clock cycles to get the frequency. For example, on the right hand side of the hyperfast traction spectra and on the left hand side of the hyperfast spectra. And to be able to do that, you have to include, after the red mode, some optical pumping to populate your atoms, all of your atoms, either in the plus 9.5 in the strontium case of the hyperfast structure, or the minus 9.5 state of hyperfast structure. If you will not do that, you will end in the line pulling shifts. So in the 87 clock, you add additional part after the remote and before the interrogation, the optical pumping. So so that's the basic interrogation and detection scheme. So you first somehow excite some of the atoms to the 3p0 state. So we think that S0 and 3p0 are grounded excited clock states. So we use ground clock state or excited clock states. So you excite part of the excited clock state here, and you want to check in detection how many atoms stays and how many atoms get excited. Because that will give you exactly the probability of the transition for the wavelength of the laser that you shine during the interrogation. So after this interrogation, you first shine off the atoms with your blue strong transition and record the fluorescence, for example, of the CCD camera. That will give you a signal that is proportional to the number of atoms that were here. And additionally, because this light is really strong, it repels all the ground state atoms from the trap. So after that, there are no longer these red atoms in the trap. What stays is the violet atoms in the excited clock state, because this state is dark for the blue light. So after that, you switch on your repumpers, the same repumpers that you were used for the blue mode, that repumps your 3p0 state atoms to the ground state. And then again, you can shine your strong blue light and record the signal that is proportional to the number of atoms that now are in the ground state. And from this, you get exactly the probability of the transition from the given wavelengths. That technique is called electron shelving techniques. Oh, for both.
But in the previous cycle for the fermionic case, next slide. So here you have the homogeneous magnetic field that you have during interrogation. Is it now just a weaker one to give you a quantization axis?
Yeah, sure. Thank you for your question. I didn't tell that. You must keep some small magnetic field to split the hyperphi levels. Yeah, and to have a correct quantization axis. Actually, and you have to separate them also to get rid of the line pooling.
I see. So not just defining quantization axis, but you want also to separate them.
Yes, both are important.
So what is the separation that you want to achieve in
100 kilohertz, I believe. I think. I don't exactly remember. No, maybe less. Sławek, what is the?
It's one kilohertz, like between two extreme states.
Okay, so 100 hertz between these. Sorry. So up to 1 kilohertz between those two states, and that actually does give you also the second thing, that if you calculate the frequencies, it's you can, and you know the properties of the atoms, you can exactly calculate what is the value of this field. Okay.
I'm just curious, that typically is going to be what, hundreds of milligauss or so, the typical biofilm?
For the bosons, you are using several Gauss. For the fermions, you are using some tens milligauss. I think. Yeah. Okay. So, for example, if we just shine the clock laser for just a given time during interrogation, so we just switch on your laser from time t and switch it off, and that's our interrogation. We can plot a really nice picture, dependence of the the probability, given that we are exactly on the resonance, on the interrogation time. So we can see that we have a really nice oscillations, and that's exactly the Rabi oscillations. So the rate of the transition between upper and the higher state. That was made in our lab, so it's not so beautiful. But I saw that picture that you really have seen the several oscillations up to 100. But still, I really like this picture because quantum mechanics. So for the so-called Rabi scheme, you take the interrogation time that corresponds to the maximum of the oscillations, and that corresponds to the pi pulse of the whole oscillation. So we call it pi pulse. And from the single clock pi pulse, you can make a really nice spectroscopy. You can see here that the width is 1.4 hertz, and it's much bigger than the width of the natural width of the line. And that's because the clock laser has some thin stability, we cannot interrogate too long. Because the laser will be fluctuating, it will go out of the frequency. So what you actually see here is not the loration by the sync pulse. And the sync is because that is Fourier transform of the rectangular laser pulse. Yeah? So that's the broadening by the finite time of the spectroscopy. And the other possible interrogation is so-called Ramsey interrogations, when you make a pi half pulse. So you, on the Bloch sphere, you excite from the ground state to exactly the middle between excited and ground state, then allow some free evolution of the system, and then by another pi pulse, you go to the excited state. And what you get is, a lot of fringes here. And so there are two basic kind of spectroscopy that are made in the optical atomic clocks. The Rabi spectroscopy of Ramsey spectroscopy. Both has advantages and disadvantages. When I first saw that picture, I asked a question, how do you know which of the fringes is correct? So how do you know which of the fringes is correct?
You can change the time.
Yeah, if you change the time, yes, then the whole fringes will go left and right. And only the correct one stayed at the same place. Yeah, and just last slide. So I told you that during your clock transition, you are not making the spectroscopy. What you're doing is you probe, if you focus on the Rabi spectroscopy, left and right half of the fringes. Because so you probe here and probe here. And if there's two probabilities, which should be about half, are the same, then it means that in the middle between is the correct frequency of the transition. If your probability are not the same, so one is lower and the other is bigger, you can easily calculate by a computer what should be the correction to move the clock laser. So it's digital lock. And the reason why the half is because there's the bigger derivative of the line, so the stronger the effect in the probability when you tune the light. Yeah, I'm sorry that I finished exactly on time and does not left too much time for questions, but I'm happy to hear them anyway.